Hello, everyone, and welcome to Lab 1 for Physics 206 and 207. So this lab is sort of an introductory lab on computing what's called percent experimental accuracy and percent experimental error, which are measurements of precision and accuracy, and also to get some exposure to graphing using Pascal Capstone for graphing. So actually, before you begin this lab, you want to make sure that you watch the video lecture discussing the measurement handout and make sure you look at that measurement handout. In that handout, I explain, what a good graph is, what makes a good graph, the things that you need for a good graph. I also explain how to compute percent experimental accuracy and percent experimental error, which is very important. This lab is really just designed to practice some of those computations. Okay, and actually this lab will not be, you're not required to write up this lab for a lab report for this lab 1. All right, so for the first part, you're told that a meter stick was used to measure the length, the width, and the height of a physics book. 5 trials are performed, right? So 5 trials for the length, 5 trials for the width, and then 5 trials for the height. And what I want you to do is to compute the average length, the average width, the average height, and then compute the percent experimental accuracy for the length, for the width, and for the height. Now, you have to be a little careful here. Remember that when you do these computations, and you should refer back to that measurement video or the measurement handout, you have to be aware of the resolution of the instrument, right? Which is how many decimal places, basically, each of these numbers are recorded to. And when you round the averages and round the average absolute deviation, it always has to be rounded to the resolution of the instrument. So in this case, it's going to be to 1 decimal place. That's really important. Okay, so you want to go ahead and do those calculations. So compute the averages and then compute the percent experimental accuracies for each of those measurements, length, width, and height. Again, if you don't remember how to compute percent experimental accuracy, please refer to that measurement video and that measurement handout. This question, based on the data in the tables, so based on these numbers, what is the resolution of the meter stick, right? So we talked a little bit about that. So you should be able to come up with a resolution. Basically, it's like the smallest length that could be measured, right, using this instrument. And you can tell that just by looking at the numbers. Okay, next, what I want you to do is to compute the volume of the textbook, assuming that it's like a box, right, which is called a rectangular solid. Well, we know that the formula for the volume of a box is length times width times height. So to compute the volume, really all you're doing is you're taking your average length, which you have in the table here, right? You found the average, times your average width, times your average height. And that will be the volume of the box. You just multiply those 3 things together. I also want you to compute the percent experimental accuracy for the volume. Now that's a little more complicated. Now, actually, let me jump over to the iPad to explain this a little more carefully. I did talk about this in the measurement handout, but let me sort of review this. Okay, so we just said that the volume of a box or a rectangular solid is equal to the length times the width times the height. So you simply multiply those 3 values together, that will give you the volume. Now, the next thing we wanted to compute was the percent experimental accuracy for the volume. So I want to find the percent experimental accuracy for the volume. So remember how to do that. That is going to depend on the formula for volume, right? If you look at this formula for volume, so I have the dependent variable here, volume, and it depends on these variables, and they're all being multiplied together, right? It's length times width times height. And the rule is, whenever you have an equation that involves either multiplying or dividing variables, it could be multiplication or division, either is going to be the same rule. If you want to find the percent experimental accuracy of this dependent variable, in this case, the volume, then the rule is you have to add the respective percent accuracies for the length, width, and height. So in this case, if I want to find a percent experimental accuracy for volume, I'm going to add the percent experimental accuracy for the length plus the percent experimental accuracy for the width plus the percent experimental accuracy for the height. And again, why is that true? Because the length, width, and height are being multiplied together to give us volume. So the accuracy for volume is going to be the sum of those three variables, right? Those three accuracies, I have to add them together. Okay, so that will give you this answer, right? Basically, you're going to add this percent accuracy, right, for the length, the one for the width, and then one for the height. If you add those three together, that will give you the accuracy for the volume here. Okay, the next part, you're told that the diameter of the basketball, of a basketball, is measured 10 times with a caliper, which has a resolution of 0.01 centimeters. So you'll see all these numbers are to 2 decimal places, right? The smallest that this caliper can measure is 0.01 centimeters. So 2 decimal places, that's its resolution. Using the data below, so using this data, I want you to compute the average diameter and then the percent experimental accuracy for the diameter. So just like before, right, you're going to find the average, make sure that you round to 2 decimal places down. Whereas before, up here, you're rounding to 1 decimal place, right? Here, you're rounding to 2. And then also compute the percent experimental accuracy. So again, just like before, you have to find all the absolute deviations, right? These will all be to 2 decimal places. Then you average these, you round it to 2 decimal places. And then when you take the average absolute deviation divided by the average diameter times 100, that's your percent accuracy. Again, if you forgot how to do that, refer back to that measurement video or that measurement handout. All right, now you're told that the volume of a sphere, right? In a basketball, you can think of it just as a sphere, is given as 4/3 pi r cubed. However, in this case, we didn't measure the radius. The r here stands for radius. We didn't measure the radius, we measured the diameter. And we know that the diameter is twice the radius, or you could write the radius is half of the diameter. So I can rewrite the formula for the volume of a sphere in terms of the diameter. And if you do that, this is what you get. You get 1/6 pi d cubed. All I did is for r here, I plugged in diameter divided by 2, right? 1/2 the diameter. And when you work this out, you're going to get 1/6 pi d cubed. So assuming that the basketball is a sphere, I want you to compute the volume of the basketball. So you're going to use this equation, right? The one that involves the diameter, because you have your average diameter here. You're just going to plug in that value. That'll give you the volume. And then I want you to compute the percent experimental accuracy for the volume. So again, here, let me go back to the iPad for a second. Okay, so we were told that the volume of a sphere, which in this case is going to be the volume of the basketball, is 1/6 pi d cubed. Well, another way of writing this, right, is I could write this as, this is 1/6, or you could write it as pi over 6 if you want, right? So you have some number, some constant, times, and d cubed means d times d times d. And we want to find the percent experimental accuracy for the volume. Okay, so first point, pi over 6, that's just a pure number, right? It doesn't have any error with it, associated with it. It's an exact number, right? Pi and 6 are exact numbers. It's only the diameter that has error associated when you measure the diameter, right? So if I want to find the percent experimental accuracy for volume, I use the same rules before. If I ever multiply or divide variables, I have to add the respective percent accuracies if I want to get the percent accuracy for the dependent variable. Well, in this case, we ignore the pi over 6, but I have diameter times diameter times diameter. I'm multiplying those three together, right? Because it's d cubed. So the rule is I have to add those percent accuracies together. So really, this is going to be the percent experimental accuracy for diameter plus another one. Plus another one. And that will give you the percent experimental accuracy for the volume of the basketball in this case. By the way, another way of writing this, you could say this is 3 times, so 3 times the percent experimental accuracy for diameter, right? Same thing as adding 3 of them together. Okay, so when you do that, that'll give you this value right here, right? So the volume, again, just plug your average diameter into this formula. For the percent experimental accuracy for volume, you're going to take your percent experimental accuracy for diameter, add it 3 times, right? And that'll give you the answer here, accuracy for volume. Okay, next it says, suppose that the accepted value for the volume of a regulation basketball is 7130 centimeters cubed. Compute the percent experimental error for the volume of your basketball. So you have, so accepted value for the volume is 7130. You can just write 7130 here, right? That's given. The experimental value for the volume of the basketball is what you calculated. That would be this value right here, whatever you calculated. And then you want to compute a percent experimental error comparing your value to the accepted, think of this, the accepted gold standard value, right? So you have to compute the percent experimental error. Again, if you forgot how to do that, you can look that up in my measurement video or measurement handout. All you're doing is you're really taking the difference between these two, right? So you do experimental value for the volume minus the accepted value for the volume. But you want to make it positive, so you do absolute value. And then you divide by the accepted value. I sometimes call this predicted or theoretical value, right? Or gold standard. And then times 100. And that will give you the percent experimental error, right? So you're just comparing your value to the accepted value. Okay, and then the last part of the lab was just to get a little more experience with graphing. So you're going to graph everything on Pasco Capstone. You can download it for your computer. There's links in Brightspace, and there is a license code there too, that so you can have it for as long as you want. You can use it for as long as you want. So in this first case, I give you a table that has time and position. And this is really the position of a cart that's moving on a horizontal air track. And it's at these positions for these particular times. So what I want you to do is I want you to plot position versus time, which means time is going to be on the x-axis and position will be on the y-axis. So time is x, position is y. Then answer these questions. Based on the shape of your graph, what type of curve would fit best? Perform that fit. Give me the slope of the graph. And actually, by asking for the slope, I'm kind of telling you what type of curve would be best fit, right? It should be linear if I'm asking for a slope. And then make sure you record that slope value here and then kind of compare it to, it should look something similar to this. Okay, I used a different program when I graphed this, but your graph should look linear like this. So you just want to make sure it matches that general shape. All right, make sure if you haven't done so yet, if you're watching this because you missed this particular class, make sure you watch my video on how to graph using Pasco Capstone. I explain all this in that video. And then the last part of this first lab is I give you another table. So now this is the position versus time data for an object being dropped, just like released in the vicinity of the Earth's surface. And for each of these particular times, this is the position of the object as it falls. So think of like 0 centimeters is right when you drop it, and then downwards positive. So now I want you to plot a graph again of position versus time. So time will be on the x-axis again, position will be on the y. And now, since this data comes from this particular equation, y equals 4.9 t squared, this is going to be like a quadratic, right? It's going to be a parabola, the shape of the graph. So like you want to do a quadratic fit. And you should find that it looks very similar to this graph. So it has this nice like parabolic shape to it. Okay, and that's it for lab one. So lab one was just practicing basically computing percent experimental accuracy and percent experimental error, and then practicing drawing graphs using Pascal Capstone. Great, thank you.